be here. It's my first time in Singapore, and I'm enjoying this series of workshops very, very much. I need to put on the mic. Yes. Yeah. So thank you for including me. This is joint work with Karen Lang and Reed Solomon. So I'd like to thank Rod for some very interesting mathematics. So there's important work in computability that connects with other areas of mathematics. So algebra, with number theory, with geometry, with analysis. And Rod Downey has done beautiful work of this kind. He's done many kinds of things, but in particular this kind. And I'd like to just mention two papers of Rod's. The first is the isomorphism problem for torsion-free abelian groups is analytic complete. This is joint with Montalban. And I like this paper very much. That's why I'm mentioning it here. The second is reverse mathematics, Archimedean classes, and Hahn's theorem. And this is joint with Reed Solomon. And this is somewhat related to my talk. So that's why I'm including this one. There are many other papers I could have chosen. So let me begin with some familiar fields and their elementary first-order theories. So the theory, the complex numbers, that's a familiar field. And the theory of it, it's the theory, we know how to axiomatize it. It's the theory of algebraically closed, it's the theory of algebraically closed fields of characteristic zero. And the models, of course, are determined just by their dimension. Then the second theory, the theory of the real numbers is a familiar ordered field. And the theory is the theory of real closed ordered fields. And there are models that are Archimedean, and these are isomorphic to elementary substructures of the reals, but there are non-Archimedean real closed ordered fields. And we could get those using compactness, but we could get them by algebraic constructions, and I want to describe a couple of algebraic constructions that produce such things. So the first is Puiseux series. So let K be a field. The Puiseux series over K are formal power series of the form, it's a sum of terms with coefficients in the given field K, and terms that correspond to elements of the rationals that are of the form I over n, where n is fixed. There's a fixed denominator in the rationals. And then the I, it could start at some negative integer possibly, and then go forward from that. So I'll write K of t, there are different notations, but I'll write K with curly brackets for the set of Puiseux series with coefficients in K. And there are natural operations on these. They're the same as for polynomials or for ordinary power series. There's a natural valuation where we take the rational exponent in the leading term, the leading non-zero term. And we take the valuation be infinity if there aren't any non-zero terms, that is, if we have just zero. So there's also a natural ordering. If the field K happened to be ordered, say it was the field of real numbers, then we look at the leading term and we say, was that positive or negative? And then that determines the power series. So there's a theorem that really goes back to Newton, who looked at Puiseux series and saw that if we took an algebraically closed field of characteristic zero, then the resulting field of Puiseux series would be algebraically closed also. And if we took a field that was real closed, then the resulting field of Puiseux series would be real closed. So this means we've got roots of lots of polynomials. And what I want to focus on is how to find these roots, so the way Newton did it. So for simplicity, I won't take the real closed case. I'll take algebraically closed case. So suppose we have algebraically closed field K of characteristic zero. And we'll take a polynomial with coefficients in the field of Puiseux series. And if this, well, of course, if the leading coefficient is 0, then 0 is going to be a root. But otherwise, Newton had a method, and it involved drawing a polygon, the Newton polygon. So we graph the pairs, so 0, and then the valuation of A0. That's the first point. And then maybe I'll take another point here. So 1 and W of, so the valuation of A1. And then maybe I'll take another one here. So this is 2, valuation of A2. And then maybe I'll go up somewhere. So 3, valuation of A3. And then maybe up like this. That's not 4, I guess. So 4. So suppose our polynomial looked like that. And we would draw the Newton polygon. It's a convex polygon, so it's a figure. So we would start downwards and then rotate until we hit one of the points, another point. Start with this first point and rotate until we hit one. And I guess with that line, we hit 2 of them, it looks like. And that's one side of the Newton polygon. And then we do the same thing. We start at this point and rotate until we hit something. So there's the second side. And then again, we would start here and rotate until we hit a point. So there's the third side. Okay, so this Newton polygon has 3 sides. And let me sort of indicate a little bit what we do with this to see something about the roots, and at least their first terms. So let's fix a side, maybe this first side, and it will correspond to some roots. So we'll take a side with first point, that 0, W of A0, and last point, the 2, W of A2. That's this point right here. So first point and last point, and we'll look at the sort of negative of the slope. We calculate the negative of the slope. So it's let nu be W of that first side, A0 minus W of A2 over the 2 minus 0. And this would be the valuation of a root. The carrier, so we've at least got the valuation part of the first term. So we want the coefficient also. So the carrier, that's the set of pairs on that side. So we've got three pairs on that side. So this one, and this one. And that's the carrier for that valuation. And then the new principal part, so this is an equation over K. So we'll write the polynomial over K. We take the coefficient of the W of A0 in A0. We take the leading coefficient in A0. And times z to the 0. Whoops, that should be a t. No, sorry, this is z. Z to the 0, and plus, and then we'll have a 1, something for that second point. So we would have lead coefficient in A1 times z to the 1 plus, and then the last term in this is the lead coefficient in A2 times z squared. So that's a polynomial over k. It has roots. And if we take a root, just choose one, then we will get a root of our original polynomial that starts off this way. So we've found a new, and our root is going to start off with, so let's say b was the root that we chose for this new principal part, and then we'll take t to the new. So this is the first term, the way Newton would find it. Okay, so we want the next term and the next and the next. So to find a second term, we'll use sort of Taylor formula. So we'll look at q of this first term plus x. And of course, we know how we could rewrite that in terms of the AIs. But we'll find a root for that. So we'll iterate this. So we find the second term by finding a root for that. And then we write the new polynomial. We take a root for that. We get the third term from the third polynomial and so on. So we continue in this way. So let's, of course, we're interested in complexity. And if we're going to say something about how hard is it to find a root of a polynomial, we have to say exactly how are we representing elements of this field of Puiseux series. So how do we plan to represent a Puiseux series? So there are different methods we could use, but what I'm going to use is a function from the natural numbers to the pairs k cross q, such that the value of f at n is giving me the nth term in the Puiseux series. It's giving me the coefficient, that's an, and it's giving me the rational that's supposed to be the exponent. So for Puiseux series, we should have a bound, a uniform bound on the denominators of the qn of the rationals. Okay, and once we know that, then that's going to imply that these qn's go to infinity. They get arbitrarily large. So we can tell when we've gone past something. Okay, so what about the complexity, even just of basic operations in the field of Puiseux series? So there are uniform effective procedures that we could apply once, given k and given two elements of k of t, these functions, s and s prime, we can compute a representative for s plus s prime. We can also compute a representative for s times s prime. Now, telling whether one of these is 0, that's pi 0, 1, because we have to ask, is there a non-zero coefficient? If s is not 0, if we know that somehow, then we can effectively find we come to the first non-zero term, and then we look at it and we get the valuation. Okay, so now the complexity of the root-taking process. So we have first a rough result that's really just blindly doing what Newton did and saying, well, what information do we seem to need? So if I is a jump ideal, and k is in there, and R is the set of elements of the Puiseux series, of the field of Puiseux series, with a representation in I, then we can show that R is algebraically closed. But this is a very rough result, and we can do better. So let's try to do better. We had to ask questions to do what Newton did. We had to ask questions. Is this coefficient 0? Is this coefficient? Once we know that, then the given term, well, we can compute it. Then we have to get a new polynomial. We have to ask, which coefficients are 0? And then we can compute the next one. So that's where the jumps are being used. So for more precise results, there's a uniform delta 2 procedure that, given k and a sequence of coefficients for a non-trivial polynomial, yields a root. So again, we want to use Newton's method, and we'll use delta 2 to decide which coefficients are 0. And again, the rest is really computable. But we can say more. So this is thanks to Reid. So if I is a Turing ideal, then for k in I, an algebraically closed field of characteristic 0, and a non-trivial polynomial with coefficients in I, that's going to have a root in I. So here, we have to do what Newton did, but we have to do it more cleverly, because we don't really know what's the next polynomial. So we have to play detective. So we could give ourselves, it's non-uniform, we give ourselves, for the initial polynomial, which coefficients were 0. We give ourselves the bound on the denominators initially. But then from then on, to say things about the new Newton polygon that we get, second and third and fourth, we have to play detective. And we have to use the fact that if we stop after finitely many steps because a coefficient was 0, a lead coefficient was 0, well, the root was going to be computable. So we can assume that didn't happen. That's as much as I'll say. So let me turn to Hahn fields. Let K be a field, and let G be a divisible ordered abelian group. Then the Hahn field consists of formal sums, and they look like the elements of the Puiseux series, except that now this T to the G, so G is not a rational, it's an element of this arbitrary divisible ordered abelian group. So the coefficients come from K, but these group elements, so it should be a well-ordered set, but possibly it's not countable. Possibly, you know, it's an arbitrary ordinal. Well, it's an ordinal that we can, a length that we could find inside G. So there's some terminology. So the support of an element, it's the set of group elements such that the coefficient is non-zero. Set of group elements that actually matter in the Hahn series, and the length of the Hahn series. So for Puiseux series, it was either finite or we went omega length. But now we could go to some other ordinal. It's the order type of the support is the length. Okay, so again, we have natural operations. So there are operations of addition and multiplication, and they're defined, again, as for ordinary power series, as for polynomials, as for the Puiseux series. We use the fact that the support is well ordered to say that multiplication is actually well defined. You need to gather together the products of monomials that are going to have the same group sum. Okay, so there's natural addition and multiplication. The valuation, that's also very natural. So we take the group element from the leading non-zero term. And if K is ordered, if we had a subfield of the reals, for example, then so is this field of this Hahn field. And has, again, what we do is look at the leading non-zero term and ask, is the coefficient positive or not? So we have a natural ordering. And the Newton-Puiseux theorem generalizes. So this is a result of MacLane. If G is a divisible ordered abelian group, and K is either algebraically closed of characteristic 0 or real closed, then the field of Hahn series is also algebraically. Question?
If G is the rationals, then you're dropping the requirement that there's a common denominator for all the
Yes.
denominators. So
Yes.
that's wrong.
That's right. Yes. Yes, there's nothing about common denominators. We could use the rationals. Yeah. Yeah. So, but we would still get this fact that the Hahn field is algebraically closed if the input field was algebraically closed, characteristic 0, and if we had a real closed field as the input field, then our Hahn field would also be real closed. So that means, again, we have roots of various polynomials. And we can ask the question, how hard is it to find them? Question?
In the definition of the Puiseux series, there was some n.
Yes, so in the definition of Puiseux series, we bounded the denominators. We allowed rationals, but they could all be expressed as as a Laurent series in t to the 1 over n for some n. So the Puiseux series are exactly gathering them together. The Laurent series in t to the 1 over n for various positive integers n. So each one has a bound on the denominators. Each element has a bound on the denominators. Now, for Hahn series, if we took the group of rationals, no bound. So we'd allow ourselves to write a Hahn series that would be t to the 1/2 plus t to the 1/4 plus t to the 1/8 plus t to the 1/16 plus ... forever. We'd allow that. Sorry. So it's... Yes. We want to think of t as infinitesimal, and we take t to the... Yes. Okay. Yeah, we don't want the t to the 1/2 plus 1/8 plus ... Yeah. Still, we would allow unbounded denominators. 1 plus 1/2, plus 2 plus 1/4, plus 3 plus a 16th, plus ... That's fine. Yeah. Okay, so if we're going to say how hard is it to find roots of polynomials over a Hahn field, we have to say how we're representing the elements of a Hahn field. And there are different ways to do it. So I'm going to use a function from an ordinal to the set of pairs k cross g, where the second component, the element of g, that has to increase with the ordinal beta. So it means I'm thinking about ordinals. And maybe we want to think differently at some points, but I'm going to do that. So here's a very rough result for Hahn fields. So if A is a countable admissible set, and K is algebraically closed of characteristic 0, and G is a divisible ordered abelian group, and these are both elements of A, we can look again at the set of Hahn series that are represented in A. So that there is an ordinal in A and a function in A that maps that ordinal to pairs in K cross G, so that we actually represent our Hahn series. Okay, so we have a set of these, and the theorem is that this is algebraically closed. Now, it may seem as if there's nothing to do here, but this took... So Karen and I started thinking about Hahn fields in 2008, and finally we know enough to know something about lengths. And the difficulty is lengths. of roots of polynomials. So let me say just a little bit. Let me say, I won't give all the axioms for all the description of what's an admissible set, but let me say a little bit about it, and I'll say what we need about it. So an admissible set, it's a transitive set with the epsilon relation, and it satisfies the axioms of Kripke-Platek set theory. And again, I won't give all the axioms for Kripke-Platek set theory, but we've got some of the axioms of ZF, but we changed some things. So the power set is dropped, and replacement and collection are restricted. So they're restricted to formulas with just bounded quantifiers. And so that we get an example of an admissible set that's maybe helpful to think about. So if we take the constructible sets up to omega 1ck, up to the first non-computable ordinal, that's an admissible set. That's, to my mind, the first one. I put omega in all. The Russians, many of them like to think of they stop at omega. So I want omega there. So what's important for us is that in an admissible set, we can define functions on ordinals by sigma 1 recursion. So sigma 1 recursion, I mean, there would be a finitary formula in the language of set theory that has only existential and bounded quantifiers and maybe it might have some parameters. And it tells us how to go from the restriction of f to alpha to the value f at alpha. So we need a sigma 1 formula that says how we do that, and then we can define functions by recursion. Okay, so that's what's important for us in admissible sets. We can do computing in an admissible set, and it's a non-standard notion of computing, but it's useful sometimes, and it's useful for us. So in an admissible set A, we've got a notion of what's CE, so A CE. It's defined by a sigma 1 formula with some parameters. And we have a notion of partial computable functions, A computable functions. So a partial function is A computable if the graph is ACE. So most often, we would define a partial recursive function, partial computable function, f on ordinals by sigma 1 recursion. Just as most of the time, in ordinary computability, you define ordinary partial computable functions by recursion on stages, by stages, finite n. Okay, so this is important for us. So this rough result says if A is a countable admissible set, and A is an algebraically closed field of characteristic 0, and G is a divisible ordered abelian group, both elements of A, and if R is the set of elements represented in A, elements of this Hahn field, K of G, represented in A, then this is going to be algebraically closed. So let me say what's the idea of the proof. So given a non-trivial polynomial with coefficients in R, we want to define by sigma 1 recursion on ordinals what Newton would do to find a root. We want a sequence of initial segments of a root. And the length of this sequence, the length of R alpha is going to be alpha. We start with 0, no terms, the empty sequence. And then we figure out by Newton's method the first sequence, and that's R1. And then we do the second step, and then we get a second term, and we put the two terms together, and that's R2, and so on. So we'll have length alpha for R alpha unless we actually get to a root, and then we'll just stop there, and we'll keep on with that fixed R alpha forevermore. So we have a sequence defined by, I'm claiming, by sigma 1 recursion. If you try to write down what Newton would do, it's really bounded searches, except for the ordinal and the function. You say there exists an ordinal, and there exists a function mapping this to everything else is bounded. Well, okay, so that doesn't prove the theorem. That says we can find initial segments, and the initial segments lie inside our admissible set. And maybe there's some clever Gandy theorem that says, therefore you get a root, but I don't see it because we're talking about well orderings here. We have to say there's an ordinal and there's anyway. So I didn't. So it seems to me that we need bounds on lengths. So, but we have some bounds on lengths after 10 years of work with Karen. So if P is a polynomial with coefficients this is a polynomial over our Hahn field, and the coefficients have lengths alpha 0, alpha 1, up to alpha n. These are the lengths, and those are present because our coefficients were present in our admissible set. And then we take gamma to be, say, the next limit ordinal after the sum of those coefficients. Then we can say that all the roots of P have length less than omega to the gamma. Okay, so this I'll come back to a little bit what went into proving this, but for now let's try to finish this rough theorem. So we have a polynomial. The lengths of the coefficients were these alpha i's, and then we can find an ordinal. We can find the sum inside our admissible set, and we can find the next limit ordinal. We had omega in, and then the ordinal omega to the gamma, that's also present. We can define by sigma 1 induction, this function omega to the gamma, and so that says that for some alpha in our admissible set, R alpha is a root. And then that means that the R alpha, we got a root that was actually in the admissible set. So maybe there's something more clever to do, but this, for now, this is what we know how to do. So I had assumed that A was countable, but we don't need to assume that. So if A is an uncountable admissible set, and we take a field K of algebraically closed of characteristic 0, and G a divisible ordered abelian group, and these might be uncountable, but they're elements of A. Then again, we form R, the set of elements of K of G that are represented in this uncountable admissible set. And again, we can say it's algebraically closed. And what we use is Downward-Lowenheim-Skolem theorem followed by a Levy collapse. So take a polynomial, and let's suppose it didn't have a root. We could write an elementary first-order statement that says there's no root. And then we take a countable elementary substructure of our uncountable admissible set. So it has these objects in it, and it believes there's no root. Now, it's not an admissible set, but we take a Levy collapse, and now it is an admissible set. Now we have a countable admissible set with this stuff, and there's no root. So the theorem holds even for uncountable admissible sets. So what do we want to do in the future? What we'd like is, given K and G and a polynomial with coefficients in our Hahn field, K of G. So K is, say, algebraically closed of characteristic 0, and G is a divisible ordered abelian group. So we want to know how hard is it to find these initial segments. So it sort of looks as if maybe for each term we need some jumps, 1 or 2 jumps, a jump maybe. And we get muddled so far, at least I get muddled so far, but maybe this week with Reed we'll become a little bit unmuddled. So we compute the first omega many terms, and maybe that takes omega jumps of the K plus the coefficients. Maybe it takes just 1 jump. we haven't come to grips with this yet. I'll say just a little bit more. What did Karen and I do to get these bounds on the lengths of the roots? So this is not computability at all. It's not logic at all unless you count ordinal arithmetic as logic. So let me say how did we arrive? A little bit, how did we arrive at our result? So let's take a subfield R of the Hahn field. So K, let's say, is algebraically closed of characteristic 0, and G is divisible ordered abelian group. And we take a subfield of it that it's truncation closed. What that means is that it has the initial segments of all of its elements. So if we have a long series, we can chop it off, some initial segment, and that has to be present. So that's truncation closed. And we'll say that it's closed in K of G, just for short, if it's truncation closed and it's also, well, algebraically closed. I said relatively algebraically closed. We could have taken a real closed field K, and then we wouldn't want all roots of polynomials. We want the ones that should be there. So it's relatively algebraically closed. So if K of G has a root of a polynomial over R, then R should have it also. We also want the base field to be included. So this closed also means, so I'm identifying a constant, so A from K, with the element of the Hahn field that's K, T to the 0. So I want to say, well, those elements are present. Okay, so that's a closed subfield. Then there's a notion of a special kind of transcendence basis for R over K. So let R again be a closed subfield of K of G, and we'll call a sequence R alpha, alpha less than some gamma, truncation closed TC basis for R. And at the same time, I'll define a sequence of subfields of K of G, sequence R alpha. So I'm going to call that a canonical sequence for R if the following conditions hold. So this R alpha for each alpha is the set of elements of K of G that are algebraic over K, I'm identifying it, together with the R betas for beta less than alpha. So I've got some of the transcendence basis, and I'm taking things that are algebraic over those. And that's R alpha. Then the next little R alpha, that's an element of the big R that's not yet in R alpha, not in this subfield R alpha. And then for each alpha, these little R alphas, they aren't just an arbitrary transcendence basis. I want to say either I'm getting something of the form T to the G, or else I'm getting something of limit length with all of the proper truncations already present. And we end with R gamma equal R. This definition is motivated by looking at a result of Morgan-Rasser, and in which they show that every real closed field has an integer part, discrete ordered subring that's appropriate for the range of a floor function. So what they did was take an arbitrary real closed field and embed it in a Hahn field, a special Hahn field, and they had to form a basis with this feature. So this notion came from their construction. Okay, so then there's a bounding theorem. So let R be a closed subfield of K of G, and suppose gamma is a countable limit ordinal. If R has a TC basis of length gamma, then all elements of R have length less than omega to the gamma. So this is what we actually used. The theorem also says what would happen if we weren't at a limit ordinal. If R had a TC basis of length, a limit plus n, where n is some positive integer, then all elements have length less than omega to the gamma plus n times omega to the gamma. And we have examples showing that these bounds are sharp. So we don't know. We have some conjecture bounds in the case R was uncountable, but we don't know really what happens. We couldn't show that the bounds that we conjectured were sharp. And the proof of this, maybe I'll say, since I still have a few more minutes, maybe I'll say a little bit what are the ingredients of the proof of this. So we have this notion of a TC basis that was important. But what we did first was look at the case where the group is like the rationals. So it's Archimedean. So there's, for any pair of group elements, there's positive ones. Let's say there are m and n, such that m times the first is bigger than the second, and n times the second is bigger than the first. So they're all in the same ballpark, the same sort of rational ballpark. So we first looked at that case, and this part one gives bounds, and in fact, for that case, no, let's see. You don't have the second factor. The second factor disappears in that case. And the proof of it used significant ordinal arithmetic. So we used some facts about well quasi-orderings, and we used some these ordinal bounds that we're getting. We used the fact that those are multiplicatively indecomposable ordinals. So having proved the result for the Archimedean group, what we wanted to do was a kind of induction on number of Archimedean classes. So if we had a TC basis and there was a new element at the end that put us into a new Archimedean class, then we would do a sort of we would look at elements in two ways. We would look at them as elements of the K of G that we were thinking about, but also as a K star of G star, where K star had the initial part of the group and what we got from that. And the G star was just the last Archimedean class. And then if our last element in the TC basis, if it wasn't giving us a new Archimedean class, then we showed that in fact the lengths didn't get any worse than what we already had. The roots of polynomials over something that was already, where the coefficients already went to the end of the group, the roots didn't go past the end of, we're not longer. They were not longer. Okay, so I think maybe I'll stop there early. So we didn't have the bounds on lengths except for the countable. So it's the results of Karen and mine saying your root is in because we know a bound on the length, and the bound on the length is in this countable admissible set. So it was for that. The definitions were, of course, those were the definition of the initial segment. Those were good in uncountable admissible sets, but we didn't have the bounds on the lengths. There.
Yeah, so this field probably has a natural topology.
we've got an ordering on it. If we started with an ordered field, there's the valuation, which also I guess gives a, yeah, the valuation probably gives a nice topology. Maybe not a useful topology, but it gives one.
So maybe you can use some topological methods. I don't know. There are books on this stuff.
Uh-huh.
Just a thought.
Yeah. Yeah. I think Noam had his hand up also.
The question is that in your proofs of sharpness, what kind of groups do you use?
So one important ingredient was 1 over 1 minus t, having a large length. We looked at certain, when is the product of two things not absorbed into the first component? So we explicitly, let's see, we used some sequences of rationals that didn't run to the end of the group, but were bounded, gave it maybe converged to the square root of 2 or something like that. So we used sequences like that to get something new and long. Yeah. Yeah. So there were some ingredients, and I guess having gotten something of one length that ran to the length of to the end of the group, we would sort of normalize it and replace it by something that was bounded, and then we could use the 1 over 1 minus whatever this was to get something longer. Yeah.